All right, let's see. Your programming test number 1 from last week. The result, we got one more test session tomorrow morning, and then after that, I will get together with the TA very soon. And then I know next Friday is a drop deadline. Hopefully nobody drop, but before next Friday, I should be able to release the feedback and also the result. But there will be some mechanism for you to submit some regrading requests in case you think there's any error on the grading. But I'll reach out to you about that. Should be next Friday, the latest. To really get a result about your marks. And for last Thursday, we missed the class, so there's a makeup lecture there about abstract data types and also stacks. You can simply go to the lecture site. You will see the row there with the pre-recorded lecture. So you got to follow that. And we should be able to continue from there with some example on Thursday. We'll see how today goes and also how Thursday goes. We definitely want to finish at least the general tree and binary tree on Thursday. Your assignment number 3 has just been released right before the class. So that one there is going to be a combination of recursion, linked tree, which we'll talk a little bit about today, and also singly linked list to really store the child nodes, which we'll also speak about today. And if you really want to get started, assignment number 3 is going to impact, well, it's going to be the coverage for your programming test number 2 later. And for your written test, which is going to happen next Thursday, not the coming one, but next week. That one there, I am going to give you a guide, PDF, and also some example question. The example questions are already on the e-class. So they will be open for try, maybe from 7 p.m., I believe. That's how I said it. But for the guide, yeah, I'm just going to give you, I'm just finalizing some detail, but I will release that either tonight or early tomorrow. But for the lecture material, it's going to cover basically everything from the beginning until up to and including Thursday's lecture. So hopefully I can at least finish the trees lecture, but I will confirm. Notes template, office hour, TA contact, they're all there, right? Resume back to normal. Any question about the course in general before I do some recap? All right, let's now do some recap, and then we'll continue. So last time, we basically finished the last bit about linear data structure. So you really want to review this table right here. We spoke about the comparison between array and singly linked list before the reading week. And we also spoke about doubly linked list, right? You really want to watch out for that. Okay, I'll leave you to study that. And then we talk about a roadmap, about the topics related to trees that we're going to talk about, but we're going to go over one by one. So hopefully for your written test, we can cover at least these 2. Okay. And we spoke about the difference between linear versus nonlinear. It's really about unique predecessor and unique successor. So these are the key terms for you to really judge whether a structure should be linear versus nonlinear. So these are the 3 linear structures we have spoken about, and this is the one we are introducing right now. We're going to dive much more into as we go for the remaining of the term. And we talk about different terminology about the trees, and with simple terms like a root, parents, and children, and also ancestor, descendants, and also siblings. So these are simple definitions. Just make sure you review the lecture and follow the example. And then let's see here. And subtree. So that's a single most important concept for you to grasp. As we go more and more algorithm on trees, you will see that every time you want to really break down a large problem into smaller problems, you always got to consider the ideas about subtrees. We're going to see more today as we try to trace about the some algorithm. We'll see. But subtree, guys, make sure you review it. It's really important. And we spoke about this particular example where we simply want to count the number of nodes in the tree, right? Over here, in order to count that, this problem here is way too big. So what we do is we look at this subtree here as a subproblem. We look at this subtree here as another strictly smaller problem. Count this and count that. Recursively get a result, add them up together, and plus 1. Right? That's roughly speaking what you're going to do. But you're going to see many patterns like this where you're going to get the recursive result from the subtrees. Okay? You can also review the tracing I kind of went through last time. Okay? And we talk about how you can calculate the number of subtrees. Basically, every node in the tree can be the root of some subtree. So the number of subtree, very no-brainer. You just look at how many nodes there are in the tree. Even external nodes can be the node or can be the root of some subtree, right? So you got to count for every node in the tree. And we talk about the difference between internal nodes over here. So that's basically a node with at least 1 child nodes versus the idea about external nodes. That will be the node without any children. So think about external nodes here is like a base cases for your recursion. When you can reach somehow into the external node, that means it's now time to somehow return from the recursive call. So at least you know there's some termination for the recursion. You don't really get any stack overflow exception. On the other hand, when you are reaching, let's say, internal nodes, that means you're still dealing with a problem that cannot be solved right away. So you have to make some recursive call on the subtree, like this, for example. All right, so these are important concepts you will see more and more as we go over more examples. All right, and then we talk about edge and path. So these are simple definitions. And the last two that we spoke about last time was about depth and also heights. Let's review that very quickly. Right? Whenever you talk about a depth, it's really about for a particular node. You don't say a depth of a tree. On the other hand, whenever you say a height, it should be the height of a tree. You don't say a height of a node. Right? You just got to be careful. And when you talk about the depth, for example, let's say what will be the depth for Vanessa? It will be the number of edges it's going to take for Vanessa to really get to the root of the tree. Simple definition, right? And then the height of a tree, so it could be the height for this tree over here, where the root is David. Or it could be the height of this particular tree, where the root is Chris. You got to be very, very cautious about when you compute the heights. You want to know where the root is for that particular tree. So that's why last time I kind of showed to you two separate examples when we calculate the heights, right? So when I say what is the height of the subtree rooted at David, that will be one problem. Another independent problem will be what will be the height of this subtree here rooted at Elsa. So the answer will be different. So the way to really understand it intuitively is not to think recursively just yet. You can think about, given this subtree here, you just divide the nodes into different levels. Each level will correspond to, for example, level 0. All the nodes at level 0 will be of depth 0. In this case, for root to go to itself, 0 edges. So that's why the depth should be 0. And then we got level 1, level 2, and also level 3, right? And then the height of this particular tree rooted at David is going to be the maximum depth of all the descendants. Maximum apparently is at the bottom here, which will be 3. So that's why the height will be 3. On the other hand, if we talk about height of this particular subtree, you're going to divide the levels also accordingly. So this will be level 0 and level 1. What will be the maximum depth for all the descendants? Well, bottom layer, that'll be 1. You can see here, when we talk about this particular tree, the bottom layer has a depth 3. Now, when we talk about this particular subtree, the bottom layer here has the depth 1. So that's why you got to be very careful about the context of calculating the heights, right? All right, any question about this? That's basically the last example we did last time. Everybody's okay? Good. So today, what I will do is I'm going to show to you at the end how you can calculate the depth of a particular node recursively. We're going to do that, and we're going to see the Java code. We're going to do some tracing, and then there will be some exercise for you to try it out to see how you can trace the heights of a particular tree. And then I'll still go over that maybe very quickly on Thursday, but it's important for you to actually try. Otherwise, you don't want to try it for the first time during the test, right? You want to try it out beforehand. All right, if no further question, let's now move on with today. Okay, so let's now see the slides. So I want to start from slide number 10, right? I want to talk about just more like a recap about the definition for tree. So tree itself is so-called recursively structured. So the structure of the tree is recursive in the sense that you can easily see the pattern of the tree structure repeating on every node. That's something I want to show to you, right? So let's try to define the trees recursively. You can also go over the slide for the bullet point, but let me dive into illustration right away. We talk about general tree, but later on today, we're going to get into binary tree as well. The definition will be very similar, but let's talk about the general tree in detail. So you got different cases of your tree structure. We talk about from simplest to the more recursive case. The simplest case will be basically like for the singly linked list. We talk about the list being empty. So now the tree can also be empty. So let's say case 0, where you have an empty tree. Empty tree simply means there's no node in the tree, right? So conceptually, you can think about it's more like an empty set, right? Just no node, just empty. Empty collection of tree nodes. Programmatically, you can think about the root, maybe some attribute declared in the node class, in the tree class, And root is simply pointing to null. So root simply doesn't even exist. If you have no root for the tree, then the tree must be empty. You might have another attribute maybe called a size. So that could be maybe just equal to 0, right? Easy to understand. That's about the simplest tree you might have, just empty. Let's look at second case. So case 1. Let's say you got, rather than empty tree, you got just one single node in the tree. So you guys learned about singleton set in 1019. Well, if a set has only one member in it, you call that singleton set. We borrow the same terminology. If you got a tree with a single node being the root, in that way we call it a singleton tree. So a singleton tree. Only one node, and that node must be the root. You cannot have a one node tree where the node is not a root. No, it's not possible. At least one node. Okay? So the way to visualize it, I'm going to be a little bit more abstract over here. Once we see the Java class, I can be a little more concrete. For now, just for conceptual understanding. So let's say you have some reference to the root. The root at runtime may point to some objects for the node. Okay? And there might be several attributes, but one of them, which I'm going to point out, is called children. Okay? Children is actually some linear structure usually. Okay? And I'll get to exactly how children can be implemented. Let me mention right away. In the lecture example, you will see children are stored in an array, which is linear. That's the example. In your assignment number 3, the children are stored in a singly linked list, which is also linear. So you're going to practice both. Okay? So for children here, let's say singleton tree, that means the root has no children. So there are different ways for you to represent this. It could be either that you simply say children is simply pointing to null. That could be one way to represent. Another way would be, let's say you guys really like array list class, for example, from Java collection. Why not, right? That's beyond this course, at least not in the programming test. You just want to reuse the library classes from Java. Nothing wrong with that. So you can try to declare something like, you might just say array list. For example, let's say tree node, something like that. Right? So that'll be your children list. And that one there, you can just say empty. Meaning that the dot size is simply going to give you 0. That's another possibility. So either the children can be null or the children dot size can be 0. It's completely up to how you implement it. So it's more like an implementation level decision you have to make, right? Conceptually, it shouldn't make a difference. Either you go for null or you go for some empty list. So these are just the implementation detail. Okay. Implementation decision. Okay. That's about the second simple case, right? Either a singleton tree or empty tree. Let's talk about the more complicated case, okay? In which case we can see some recursive structure for the tree. So case number 2. When you got at least 2 nodes, that means at least the root itself plus another node, at least. Okay. Now, how do we visualize that? Let's try that out here. So you have a root which exists that will point to some node objects, which has several attributes, and one of them is the children. I'll just say C, just for short. Okay, children. And let's say we have an array of tree nodes as the children. Okay, an array always fixed size, starting from index 0, index 1, and typically, as we will see in the example, you may just define some constant to say what's the maximum number of children for each node, right? It can be 10, can be 100, right? So 2 all the way to maybe some constant maximum minus 1, right? That's a maximum index you may have. So this is how a single node would look like. We don't see the recursive structure just yet because we haven't really elaborated on how each element in the child list will look like. And let's now do that. Okay. Let's now look at children here first. How do we declare that? It would be something like this. For example, we might simply say tree node. Here, I'm not putting any generics just yet, right? Let's not bother with that detail just yet. I might say tree node array. So each element in the array, at index 0, index 1, index 2, each one of them is just going to be another tree node. This is where the recursive structure is going to come into play. Okay, let's visualize that. For example, you can see that at index 0 over here, it's going to store the tree node representing the first child node of the root. So I might just put, let's say, for example, another node right here. Okay, this is just another node. And also, let's say I got another child here. Okay, let me use a slightly different color. Let's say one here. And then that one there is also pointing to another tree node over here, right? And we know that for each node itself is also going to have their child, like a grandchildren, basically. So this one here is going to be just some array. And also for this node over here, also you got a list of child nodes. That one there is also going to be something like that, right? Let's see where the recursive structure comes from, okay? You can see that over here, this pattern over here of a node is being repeated right here for the first child. Because you can see the node itself and also child list. Also the node itself and child list. And this one can go on and on and on, depending on how deep the tree is. And this is just another one here. Okay, so you can think about this guy here. This one here is really the subtree rooted at the first child. And this one here is really the subtree rooted at the second child, right? So this pattern here is repeated one time and two times, and it can be as many times as necessary, depending on how large the tree is. All right, any question here about the general tree structure? Okay. Of course, for your assignments, you should really know how to construct a tree, and then also how you're supposed to process the tree recursively. That's an exercise you have to struggle through. Okay. All right, if no further question, let's now go over some terminology quickly, and then we'll look at Java code. Okay. Let's now go back to the slides. So we have just gone through slide number 10, just about a definition. You can look at a little bit more detail, right? Pretty much consistent with what I just presented. Okay. And then this slide here just showed to you whenever you want to talk about legal organization for a tree, basically from each node, let's say, let me show you some illegal one. Why? Let's look at this one here, right? Right here, where my cursor is. Why is this particular tree illegal? It is because if you want to go from one node at the top, the root, go to the bottom node, in order to be a legal tree, there should be exactly one path to go there. If you got more than one path to go from one node to another, it's not a tree anymore. For example, for me to go from this root to this bottom node, I can either go for the left and here. I can go to the right and then here. I got two possible paths. So it's not a tree anymore. It is something called a graph, which you will learn not in this course, but in 3101. All right, so just make sure you understand what a legal tree is and what an illegal tree is. So here, the line here, just talk about the definition, right? Okay. All right, some very quick terminology about order versus unordered tree. What is really an ordered tree? We say that a tree is ordered if among the children, there is some meaningful linear order among them. Meaning that this is like a concept about which comes first, which one should be the successor and which one should be the predecessor. If there's such a meaning imposed on the child nodes, then the tree should be ordered. Let's see one example, very straightforward. So let's say a book. Let's say we got some table of contents, right? So that's more like a tree structure. So this is like order tree. And for order tree, if you look at, for example, the child nodes at the first level right here, right? So under the book, we actually got a preface, which should come before part A, which should come before part B, and which should come before references, right? That's like order over here, right? So in the order tree like this, there is a linear logical order between A nodes, child nodes, and etc. Right? You can see under Part A, Chapter 1 should really come before Chapter 2, which ultimately should also come before Chapter 5, right? There's an order there. So that's an order tree. On the other hand, if there's no such ordering imposed among the child nodes, there will be unordered, as simple as that. If you guys want to try, if you log into your REST server, there's a command, I'm not sure if you know about it, you can try. Go to your REST server, and then there's a command called the tree command. Okay? Basically, type the tree, and then you're just going to specify some path over here. For example, you can cd into a particular directory, and then you can simply say dot, the current directory. That one is going to show you the tree structure of your directory. Okay? You can give a try. That one shows you just about the tree structure. And in this case, we are saying that let's assume that between the directories under, let's say, under the courses root directory, between the courses, there's no order. So we don't really say this particular course should really come before this course. There's no such ordering, let's say. In that case, you'll be unordered. So there will be no ordering. And something also for you to consider. For an ordered tree, since the child nodes has no ordering, in that case, if you don't really have any duplicates, you may store them rather than in an array list, you can also store them in a set, right? Because there's no ordering. So I'm going to say, for example, you may store them in array list, which is absolutely fine, or you simply store them in hash set, assuming that there's no duplicates. Okay, you can make a judgment. On the other hand, if you talk about order tree, it must be a linear data structure, it cannot be a set. All right. Here, I'm just going to put array list. Just an example. Okay. But in the assignment, you're going to use singly linked list, not the array list. Okay. All right. Very simple definition about order versus unordered trees, right? Let's now take a look at some Java code. Okay. And then I'm going to explain some line there that seems a bit crazy when you first see it, but I'm going to go over slowly. So if you go back to the slides, there's an order tree, there's an unordered tree. Okay, simple definition. And let's talk about tree node, which is part of what you're given in the starter project for assignment number 3. Okay, tree node. Let's now talk about that class in detail. Okay. So to start with, you can see we got a class called tree node right here. And you can see that it's generic, right? We got a generic parameter for that. And then we got some element attribute, just like a singly linked list or doubly linked list. After all, the reason that we have data structure is because we want to store data elements. So you must have data. It doesn't make sense if you don't store any meaningful data. And if you instantiate this E to be string, then this element here will be string. If you instantiate E to be integer, then that will be integer, etc. Right? That's kind of the generic lecture you're supposed to study. Okay? And let's look at the next two attributes here, which both contain some tree node right here. Okay? So you can see we got tree node here, and we got tree node here. A single tree node is the parent link, right? Just basically point upwards you can think about. On the other hand, you can see children over here has the array right here. All right? That tells you you may have more than one child nodes. That's what a general tree looks like. Okay? When we get to the binary tree, you don't necessarily need to have an array. But that's something we'll get into. So you can see over here, you got an array. Right? So that's a linear data structure, children. There are two more things over here, which I'll also illustrate to you. Because we're using an array, you have to somehow keep track of where you are in the array. Because array, when you first create it, it's going to be fixed size, right? So first of all, we can talk about the size over here being some maximum, right? Let's say some magic number, just 10, just for now. Let's say maximum number of child nodes will be 10. We got another counter over here, which is going to keep track of how many child nodes we have stored so far. And got to watch out for this value over here, right? I'm going to show it to you, right? It's very easy to understand. I'll get there. And we got the tree node constructor over here, right? We just initialize We just initialize the tree node with the element that being stored. Set the elements, set a parent to be null, and then we have to initialize the children array. Okay? And this line here, let me just highlight it just for now. This is a very ugly workaround that we have to write in Java to make it work. I will turn to a new page just to show you how it works, but bear with me. Let me just go over the rest of the class first. And then we got the standard accessor. You can get the elements, you can get the parents, you can get the children. Okay? And also you can also got mutators for that. And there will be some exercise over here you can also try. How you can remove a child in a particular index. In that way, you have to remove from the array, which we know is a linear operation. Okay? Okay, so what we're going to do is we're going to go into this particular one. Oh, before that, let me just visualize very quickly about the NOC very quickly. Let's say I have some node called n. I have created some node called n. And then the parents may point to some other tree nodes. I can just do that. I'll make it more concrete as we trace some JUnit test case, but for now, just a visual. The parents may point to some node. Let's say this node here is not a root, so the parent is not null. And then the element might be storing some contents. For example, let's say string. I can say maybe Alan. And then I got children here. Okay, let's say this line works. Okay, I'm going to get into the logic for this line in a moment. It works, that means children is going to be initialized into an array of size 10 because I got 10 right here, right? So now I want you to see two things over here. Number one is when you look at n.children length, that one is always 10. Agree? Because never changes its size unless you grow it. Okay? That's the length of the array. On the other hand, NOC over here is going to be a little bit more dynamic. It's going to reflect about how many child nodes we have added into this particular node. All right? At the moment, we just got NOC and NOC being equal to 0 when we first create a node. There's no child nodes just yet. But let's say if we decide to add one child to this node here. In that case, as soon as we have added the child node, we're going to update the NOC from 0 to 1, whereas the length remains to be 10. Agree? And then let's say we want to add just another child node right here. In that way, we're going to increment from 1 to 2. Right? So there's a very simple property here. You can think about n.NOC is always less than or equal to, well, strictly less than, actually. Strictly less than n dot, beg your pardon, should be less than or equal to children dot length. That's a very simple property that you can grasp. So in this case, NOC can go all the way up to just 10. In which case, NOC tells you you cannot really add any more child node into the array unless you grow the array. But that's going to be another story. All right, before I get to this line here, let me recap very quickly. So when you study this class here, number one, make sure you know where we're going to define the tree nodes right here, a single tree node for parents, an array of tree nodes for children. And also we got element, also it's generic. And then understand the difference between NOC here and also the length of the array, which is always fixed. Okay, I might ask you some question about it, maybe in the exam or the written test. But I got to make sure you kind of study that. And you also got to compare, when we talk about doubly linked node, right? We only got 2 pointers. We got previous and next. Compare these two with maybe the parents and the children. We're going to see exactly what the difference are. Okay. Any questions so far? All right. Let's now talk about this line here, right? Let's now talk about this one here. Okay. This line here, I would suggest we talk about it a little bit more systematically. Okay, so you can really grasp the idea. So let's use two classes to really illustrate the idea. Array stack is part of your makeup lecture, so make sure you catch up with that. But I'm going to review very quickly. Array stack, which is generic, and also the tree node, which is also generic. Let's use these two classes example. Okay. And the problem really lies in when you want to initialize or you want to initialize an array of generic type. It's going to be a little bit tricky. Right? Let's talk about a simple case here. So you can see the, let's see here. First of all, you can see data simply got of type E, which correspond to this E right here. This means at the compile time, if I instantiate this E here by string, this is going to be a string. If I instantiate this by an integer, this is also going to be an integer, right? That's something we know pretty well. And you can see E here is by itself. It's the type of each element of the array. Okay? And the problem is, how do we instantiate the array of type E? Intuitively, you might be thinking as follows. You might be thinking, well, just like, let's say if I declare E rather than E, it may be a string array. You might just say data is assigned to new E. And then of size maybe 10, let's say. That's a very intuitive thinking, which I know what you meant. However, it doesn't work in Java. All right? If it works, we don't even need to talk about this page. Okay? Doesn't work. The very brief reason is because generics was only introduced to Java in the very late stage, in the maybe in version, I don't even remember, maybe version 4, version 5, definitely not the initial version. It's not part of the initial design for the language. So after they kind of introduced the generics into the language, they wouldn't have enough support behind the scene to really do this line over here. They just cannot. So what we got to do is some workaround. In simple case like this, if you got, for example, an array where the element type is simply just E itself, what you do is, you guys learned about casting, right, from 2030. What's going to work will be something like this. You can say data is assigned to, okay, rather than doing this, new E, you can say new objects. So Java wouldn't allow you to put any class that's unknown. You have to put a known class. In this case, what's the most general class in the top of, on the top of the inheritance hierarchy? Objects, right? You put objects right here, and then of size 10. If you do this, also it's not going to work because object here is not compatible with the data which is declared to be E, right? It doesn't work. So what I got to do is do a casting. So what you would do is you're going to cast that thing into E. So that's what you got to do. All right? This will work. And I think I also mentioned that in the makeup lecture, right? So it's more like a recap for you. So this is actually going to work. All right? And it's also very important for you to remember, after this line here, let me just write a little bit some lines over here. So let's say you got array stack, I'll just say AS, array stack. Let's say we in some application code. Array stack, and then I'll put string. Okay, and then I'll say S, standing for stack, is new array stack. All right. So you can think about this part over here. The constructor is exactly what we were talking about. And as part of the constructor, it's going to execute this line to create the array. Right? That's what you're going to do. Okay? There's some confusion from your fellow student in the morning session. I just want to clarify that in a more explicit way. Okay? Doing this line over here is not going to compromise any of the benefits of using generics. Let me show you why. Okay? Let's say this constructor call is going to execute this line here. So what's going to happen is it's going to create at a runtime, for example, S is going to point to some array stack of string. And the data is actually going to point to an array over here, each one of them. And in the beginning, every element there will just be default value, none, right? Etc. You don't see any object just yet, right? You just know in the beginning. And then if I try after the initialization, if I try s.push, right? I assume you already watched the lecture, right? Or if not, you can catch up. If I say push 23, it's not going to compile because this line here already instantiate the E to be a string. In that way, push somewhere is going to expect string rather than integer. So it's not going to compile. So that's what I meant. Even by writing a workaround like this, so when you see how to use a stack, you will still get all the benefits of using generic parameter, right? You wouldn't lose that, right? So this one here is not going to compile. On the other hand, if you write s.push, let's say Alan. This one here is good because I instantiated the parameter as string, so now I can push string. That one there is going to, let's say the front is the top. I can remove that to be Alan. Okay, one more thing to say. If I look at this particular element over here, and you guys learned about static type versus dynamic type, right? Back in 2030. I assume you still understand, you still remember that. If not, you want to catch up. You might be tested something about it because there's a polymorphic stack component in the makeup lecture, which you can study that. If I look at this element over here, you want to think about what's its static type and what's its dynamic type. Static type over here is going to be string. Which simply just correspond to whatever generic parameter E has been instantiated into. What about dynamic type? This, in this case, happened to be the same because you just have pushed the string into the array. Okay? Dynamic type is also a string. Okay, let me recap very quickly. When you have a generic parameter declared as part of the class, if you got some linear collection like array, and the element type is simply generic parameter itself, if you simply write a line like this, it's not going to compile because Java wouldn't allow some unknown class to be put here. What you should do instead is by using the most general type at the top of the inheritance hierarchy, objects, and then cast that into here. But just remember, whatever compilation benefits you can get from generic parameter, you're still there. So if you try to push any elements of the type that's not compatible with the instantiated type for generic parameter, it's not going to compile. Okay. All right. Any question about this? All right. Let's now talk about the second line here. All right. This is where the fun is. Okay. Let's say we have another class that's generic. We got E here, but now we got children, which I said earlier. Now the children is going to be an array of tree nodes. All right. So now I want you to do a very close comparison right here. If you look at here, the element type for this array here is just by E. The element type for array here is not just E, but it's actually E wrapped within another generic class. You see the difference here, right? So this one tells you if you do something like this, it's also not going to work, unfortunately. All right. So first of all, let me write down some highlight here. So in this element type here, the generic parameter E is wrapped within the tree node class. This will make it more complicated. We just need another more general workaround. That'll be the ultimate one we need to write. But let me first of all show to you. Over here, if you try to write over here, if I say children, if I follow the logic of what used to work, equals, let me say Tn for tree node. If I say tree node of E and then array, and then I say new objects, and then 10. Right? I'm following just the same logic as this one here. But this one here is not going to work. Right? As I said, it's because the E here is not by itself anymore. So that's why it's not going to work. So I want to write it out explicitly and tell you that it's not going to work. What will be the ultimate solution? The ultimate solution is we have to use a library class called array. From that array class, we have to somehow call its static method called new instance to return us an array instance. I'll show it to you. Okay? So the ultimate line you should learn how to write goes like this, which I'm going to put here. Let's say here. Okay, right here. Okay, so this will be the ultimate solution. We're going to say children equals, okay, we're going to use the array class. Array dot. So we are using a static method from there. So feel free to look up the API for the array class. Okay, array the new instance. And it will take two arguments. Okay, the first argument, I'll talk about it in just one moment. That one it has to do with the type. The second element here, the second argument is about the size of the array. In that case, we can just pass 10, corresponding to the 10 over here. Right? Before I tell you what this is, right? If you look at the return type for new instance, it's going to return just an object array, meaning that we should really do a cast. All right? It's just the API definition. Okay? So here I'm going to say the tree nodes of type E array. I'm going to cast that. All right? Just confirm. That's exactly what you saw, right? We got some cast over here applied to array.new instance, and then we say the number, which can be 10, can be some integer. Now I'm going to explain what this guy here really means. All right? That's the final bits. And this guy here, basically, I want to say what's the type of the array elements. Each element should be a tree nodes of E. How should I pass that? If you simply say tree nodes of E right here, it's not going to work. There's no such valid expression. What you're going to pass will be the safest way. I'll write it down here. This. By the way, you guys have seen this keyword before, right? What's this? This basically is a context class where you're writing this line. Okay? So when I write this keyword here, because I'm writing this line in the context of the tree node class, this is referring to exactly this class here. Okay, right here. Okay, so let me just make it more explicit for you. So tree node over here is really this. And then I'll just say get class. Get class is just going to get a relevant information about this particular class, which array.new instance will need. Dot get class. Right, so that's the ultimate line you have to know how to write. In case the array element is not just E by itself, but it's wrapped within some class like a tree node. Right? All right, guys, any question about this? Yeah?
So what does it say again in the pink parenthesis in the last line?
Yeah, of course. Yeah, sure. You mean, oh, sorry. Are you talking about right here?
Yeah.
Okay, sure. If you look at array, the new instance over here, the return type is going to be an object array. Let me write it down. If you just look at just this part here, array, the new instance, the return type is simply just an object array. However, the children here is not an object array. It's an array of tree nodes. So we still want to cast that into tree node array. That's why we're going to do it. So as far as the new instance return value is concerned, it's simply just an object array, which will not be compatible just yet with what we want to assign to, which is a tree node. Oh, tree node here. Okay, that's why. All right, very Java oriented, but since we're using Java as a programming language for this course, that's something you would need to know. Okay. By the way, should you worry about this in the programming test? The answer is no, because you wouldn't be allowed to use array anyway, right? But in the lectures, I think for the lecture example, you should know this, because who knows, right? You may want to use array of tree node at some point of your developments, right? Okay, that's important to clarify. You guys can try and then experiments. All right, let's now try to do some node construction, okay, if no further question, okay. So what we just spoke about was this class over here and that crazy line in line number 13, right? That's what we just explained, okay. And then let's now talk about, and this one we also covered, let's now talk about this test case, which is going to build a connected, like a tree, connected tree node, basically, like how we build a chain of nodes like before. Okay. All right, let's now say we want to build the following structure. Let's say we want to build Agna being the root. And then that one there has two child nodes, let's say. We got Elsa, and also we got Anna. Let's say that's the tree we want to build, right? The idea is very simple. Basically, you want to create node number 1, node number 2, node number 3 with no connection just yet. And then set a child nodes and set a parent node. That's basically the layout we're going to see. All right, let's now go over these steps over here together. Okay, and I'm going to create 3 nodes in total. So let's say this one here, I'll make it green. This line here, got to create a first node, and then the second node, and also the third node. And one thing you can note here, the constructor for the tree nodes, we're just letting it take one argument, just the elements. If you want, you can feel free to extend for your developments with another argument, which will take maybe the parents and even the child nodes if you want to, right? It's completely up to you, right? Let's see how we can do that. So we're going to create 1, 2, and 3 nodes. Okay, I already got something here that can save some time. So let's say 1 node right here, and then I got another node here, and I got another node here. Okay, 3 of them. Okay, the first one is going to be the green one. Let me see here. That's the first one. And the second one for Elsa, let's make it pink. There we go. And the third one over here is going to be orange. Okay, there we go. Good. Okay, let's now go over the step. Oh, there we go. Let's be a little bit more perfect. There we go. Okay, let's go one by one. When we try to create the green nodes, the only thing we set is the element here. So that means the element here is going to be Agna. And the parents is going to be just null to start with. Okay, oops, sorry. All right, null. And the children, after executing that long line workaround we talked about, right? We got this array right here. And at the moment, you can see the array has been already fixed size, which is 10. But what about NOC? 0, right? The number of children. Just remind you, NOC is one of the attributes here, right? So let's now just put NOC aside. So NOC will just be 0. And of course, this node here has a reference called Agna. All right, so that's the first node. And the second node is called Elsa. So I'm just going to put Elsa for the second node. And that one there, we got the elements, which will be Elsa. And the parents will just be null. And the children, right, you can see still fixed size, but NOC will be 0. So you can think about Elsa.NOC equals 0, no child. Similarly, we got Anna here, and the parents is simply pointing to null, and the elements is Anna. And you can see that Anna.NOC is also equal to 0. Right? We create 3 nodes separately. They have no connection just yet. And let's see, the following 4 lines are going to make them connected together. Right? Let's see the first 2. Number 1, oh, sorry. Let's say number 1 here, number 2 over here. Number 1 there, we say Agna, the add child, Elsa. What it will do is So ECNA is right here. If you want to add child ELSA, that means at index 0, it's just going to point to wherever ELSA is pointing to. Right here, right? You will also know how to implement this in Java, right? It's very basic operation. This will be step number 1. As soon as this is done, we will also expect NOC to be updated from 0 to 1, right? So that means you got one child for that node. And for step number 2, ECNA, the same root, add child, ANA. That means index 1, the second child, is now going to point to right here, where ANA is pointing to. At the same time, we're going to update NOC from 1 to 2. So now you can see NOC here really reflects about how many child nodes we have, which is not really the same as the fixed size, just 10, right? It's always 10. So you shouldn't really look at array.length to see the number of children. Right, so that's about step number 1, step number 2. But we are not done yet. We still want to set the parents. Right now, we say that ECNA has the first child being ELSA. But ELSA's parents is null. That doesn't make sense. Right? There should be some symmetry over here. So we'd say this will be step number 3, step number 4. ELSA, the set parents. So ELSA, the set parents, rather than pointing to null, is going to point to ECNA right here, right? And for that one there, we don't really update NOC because we're only updating parents. We're not updating child nodes. Similarly, so this will be step number 3. Step number 4, ANA, the set parents. So ANA, the parents, rather than pointing to null, is going to point to here, right? And that's it. Right, it's a very simple tree structure here that will give you the idea, right? Of course, if you want to build a more complicated tree, you will follow just a little bit more nodes and set the references accordingly. That's what you got to do. All right, questions? We're good? All right, and you guys can also easily just follow through the assertions here in the JUnits, right? They are very easy to follow, right? Just to make sure the tree structure we have built is really corresponding to what we hope for in the beginning. Okay, very good. Okay, if no further question, let me see. I would suggest the following. I want to do one more Java code. I just want to use this code over here and try to show to you how you can actually run some recursive algorithm on a tree. Right? We're going to use a family tree example, but we're going to still use some Java code. Let's do that quickly and do some tracing, and we'll take a short break. And then we'll come back and do binary tree. Okay. Okay, let's see here. Okay, good. All right, so let's now take a look at here. So we are now done with slide number 16. Okay, let me give you a very quick walkthrough. So slide 17 gives you the problem about given some node. I'll speak about this one in detail. That's about computing the depth of a node. So you will see some conceptual hints, and you see some Java code, which I'm going to go over with you line by line. And there is some test cases, and the code is already on the lecture site. You should really download it, import to Eclipse, and play with it. It's also going to help you with the assignments. Okay, we're going to go over this test case in detail. So we're going to do the tracing as well. So this will show you a different way of tracing. If you recall how we did the tracing in class for the split array, we draw the recursion tree. But the thing is, we already got a tree over here. So sometimes you may not need to redraw another tree to really do the tracing. So what I will show to you is what's really shown here. I'll show you from scratch. Is something called unfolding the recursive definition. Right? Somehow it can also give you some very good insight about what's being computed. In some way, it can also help you understand about how things are going to work at a runtime. I'll show it to you in just one moment. So that's the example we're going to do today. And before Thursday, I would suggest you try to digest about how the depth is going to be computed in class that we're going to talk about in class today. Before Thursday, I'm also going to talk about how you can compute the heights, but very quickly. So before Thursday, also take a look at this one. So we wouldn't cover that today. We'll cover that very quickly on Thursday. Okay, that's the heights. So that will be up to also slide number 22. All right. Let's now take a look at depth. There we go. All right, guys, look at this fragment of code for 1 minute. Very simple code, but it's recursive. just for 1 minute. And then we'll trace that together. We'll understand that as well. Okay, 1 more moment, and then we'll go over that code in detail. Okay, everyone's good? Okay, at least I've seen the code. All right, let's take a look. First of all, let's convince ourselves it's really recursive. You can see we got depth over here, and then we got depth over here. It's calling itself, right? So it's a recursive method. And then let's look at the input here, which is very common. You're given a single node right here. You can see a single tree nodes, n. All right. So here, whenever you're given just in the case of the programming test or your assignments, when you're given a singly linked node, we said that's usually the beginning of some chain of nodes, similar. So here, if you're given a single tree node, it will be the root of some subtree, right? Similar idea. I'm going to write it down. So the node n will be the root of some subtree. For example, n in the beginning may just be this. As you try to run recursion throughout the tree, n might be pointing to here, n might be pointing to here, and also might be pointing to here as you make more and more recursive call, right? That's something you want to keep in mind. Okay? But to start with, it should be the absolute root of the tree you're trying to process. That's number one. And then we talk about some base case right here. The base case is to say, if you want to calculate the depth of a node, if the node here is already the root, by definition, it takes no edge to really go from the root to itself. So that should be just 0. That's the simplest case. You don't need any computation, right? By definition. So this one here is the base case. Okay, so this one here, the depth of the root is 0. Base case. What about recursive case? For recursive case, apparently there's an else part, and we can break it down into 2 parts. Okay. Let's say I got a depth over here, and also I got 1 over here. And somehow I'm combining these 2 results together as a return value, right? Let's take Vanessa as an example. Vanessa, okay? Let's say I try to figure out the depth of Vanessa. That's what I'm passing. The depth of Vanessa. So V here is Vanessa, D here is depth, okay? Somehow, Vanessa is too far from the root. I cannot compute it right away. Because by definition, depth will just be the number of parent links you have to go from the nodes all the way to the root. Somehow, Vanessa is too far from the root. So I cannot solve this problem right away. So what I can do is, I can follow from Vanessa by just 1 link of the parents. So I'm just going to say I can follow just 1 link, 1 here, which corresponds to the 1 here. And then the rest of the problem is going to be a subproblem, which I can I can make a recursive call of depth on. So that one there is going to be this part over here. So this part here is the remaining part to really get to the root. That's a subproblem. So here I'm just going to calculate the depth of Vanessa's parents, which will be Elsa. Okay, recap. In order for me to calculate the depth of Vanessa, I'll simply say, first of all, let Vanessa get to her parents, which will take 1 link, plus whatever the depth I can recursively figure out for Elsa, who is the parents of Vanessa. Right? That's basically what I'm doing. Right? Right here. You can see n get parents. In this case, n is Vanessa. Vanessa that get parents will give you Elsa, right? Etc. Okay. That's really conceptually what this code is really trying to do, but let's now trace it. Okay. If you look at the JUnit test code I made available to you, I got many possible nodes, you can actually pass over here, right? You guys should really try it out and try to trace it, but I'm going to do one completely with you, which is this one here. Okay, Vanessa, which I already told you, right? Let's try to see how the unfolding is going to work, okay? So I want to compute depth of Vanessa. I want to know whether or not it's a base case. I'll check to see whether the parents is null. Apparently, Vanessa parents is not null because it's Elsa, right? So here you can say Vanessa's dot, okay, just say dot get parents. Dot get parents is not equal to null. So I know that I should really go to the else part. What I will do is going to be 1 plus. And the 1 here is really the 1 I spoke about earlier, right? To get to the parents. And then I'm going to get to Elsa. That will be the depth of Vanessa, the get parents will be Elsa. Are we okay with the first unfolding here? I'm basically unfolding the definition here into here. Because I know that Vanessa, the get parents, is not equal to null. So I should really apply the definition in the else branch, right? That's what I'm doing here. How do we unfold this guy here? You want to know whether you will fall into the if or the else, right? Let's check again. So we know that Elsa, the get parents, also is not null because it's quiz. Not equal to null. So what I would do is, so I still got this 1 here from before. And also, now if I want to calculate the depth of Elsa, because I know it go to the else branch, it's going to be 1, which corresponds to getting to Elsa's parents and the depth of quiz. Okay, is going to be 1 plus the depth. Elsa's parents will be quiz. So you can think about the orange line is really this parent link. In order to calculate the depth of Elsa, I want to get the parent link first and then calculate the depth of quiz. All right. And how do we unfold this guy here? Because quiz, the parents, is still David, not now. So we're going to unfold one more time. Okay. So we're going to say, okay, plus over here. We still got a 1 here. We still got a 1 here from before. And now to unfold this guy here, I'm just going to write 1 plus, right? You can think about the 1 here is for Chris to go to the parents, David. And then that one there should really lead me to the root, which will be the depth of David. Let me write better. All right, we're pretty good because now you can see this one here is reaching the root. David dot get parents will be null, right? That one is going to be 0. So this would mean this call over here is going to give me 0. Unfolding terminated. Now if I add up the numbers, I got 1, 1, 1, 0, which will be 3. So that's the final answer you will see right here. So somehow this recursive method, of course it works, but you really want to see by using this recursive definition, it can somehow nicely unfold into the number of parent links you have to follow by the input node all the way to the root. Right? So that's really something you want to see. So the exercise you should really do is, number 1, try it out at least a few more over here, right? Try different nodes in the tree, number 1. Number 2, before Thursday, take a look at the heights definition, the Java code here. Right here. So on Thursday, I'm going to assume at least you look at the code and look at the test cases, and then I'll trace one example quickly with you on Thursday, just to wrap up, right? But you really have to make sure to digest the depth before you see the heights. Very important, okay? All right, any question about this one here? Any question? We good? All right, I got only two more things to say. One is to really introduce you very quickly about binary tree. And the other one is I want to derive a mathematical formula together with you that's going to be so important for Thursday. Okay? But before that, why don't we take a very short break and take attendance? Two more things for today. So let's now talk about, first of all, I want to start exercises. So these are just calculating ancestor descendants. I'll mention them again for you to try on Thursday. Okay? Binary tree. Okay? Binary tree is not difficult because if you understand general tree, which got arbitrary number of children, binary tree tell you you can get at most 2. That's the difference, really. Okay, let's now see some definition, and then I'll talk about some formula, so you will get ready for Thursday. A binary tree is order tree, right? We talked about order tree before the break. Order tree tells you the order for the children matters. In the case of binary tree, we only got 2 children at most, left and the right. The order matters. And at most 2. It can be 0 children, external nodes, or it can be 1 node, or it can be, so it can be 1 child or 2 children, right? So that's the definition. But you can look at the text. Let's now try to talk about similar recursive definition. By here, I'm going to reuse a little bit about what we said earlier before the break. So for the 2 base cases about empty tree and also singleton tree, it's just the same as before. So for those 2 parts, I'm not going to repeat, right? I'll just list them. But the case number 2 will be a little bit different. That's something I'm going to talk about, okay? So let's go to the binary tree. So case 0 will be empty tree. And case 1 will be a singleton tree. Visualize the same way. And let's talk about case number 2. When you got at least 2 nodes. How is that going to look like? Very similar. So you got the root over here. And it's an order tree. Think about you got 2 links only. You got something called left. You got something called right. Left comes before the right. And then the left node and the right node over here. And the subtree rooted at the left. There's another subtree rooted at the right node. And each subtree can be arbitrarily big, which we'll speak a little bit more about mathematically on Thursday. And we have some name for this. This particular subtree rooted at the left child is called a left subtree. Or sometimes we just say LST, left subtree. Or we got another one here, which would be the subtree rooted at the right child. It's called right subtree. RST. All right, I'll continue more about the pattern. But for the remaining about 9 minutes, I want to talk about one mathematical formula together with you. So you can digest about the formula before Thursday. Thursday is going to be very math heavy. All right, but so I want to get you ready. Do you guys remember geometrical sequence? And I mentioned that briefly when we talk about arithmetic sequence. Now is the time to talk about this guy here. There's no data sheets for you on the exam or written test. Either you memorize the formula, which I wouldn't recommend, but if you really forget about the formula, I'm going to show you how you can derive it within 30 seconds. Of course, when I derive it, I got to explain. It will take more than 30 seconds. But when you derive it by yourself, it's going to be quick. You just got to see the reasoning over here. All right, let's now see this in detail. Geometrical sequence basically got initial term, and also it got something called common factor as opposed to common difference, and also the number of terms. One example here. So let's say 1 plus 2 plus 4 plus 8 plus 16 plus all the way to 1024. Okay? And the very first term over here, we said that it's called the initial term I. And between the terms, you can see from 1 to 2 is multiplied by 2. From 2 to 4 is multiplied by 2, and etc. So that's called the common factor. Right? Easy to see. Of course, common factor can be 2 or 3 or 4, whatever. Okay? And there's another term called a K, about how many terms there are. Can you guys look at this pattern here and tell me how many turns are there in this sequence here. Don't tell me 10, 24 turns. I don't think so.
10, 12.
Oh, you guys are getting somewhere, okay? I heard 10, I heard 12. Wrong. 11. Okay, how? All right. This guy here, 2 to the power of 10. All right? 2 to the power of 0. You basically go from 2 to the power of 0, 2 to the power, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, all the way to 10. From 0 to 10, how many numbers? 11. Okay? You guys can think about it. Okay? I'm going to write it down here. So K here will be 11. This sequence here is very relevant to binary tree because you can think about the number of nodes in each level, which we'll see on Thursday. Okay? But let's focus on this mathematically first. Now, first of all, we know there are 10 turns over here. And the next question is, what would be the sum of all these numbers over here? There's a formula for that. Okay? I'm pretty sure I have seen that sometime in your life. I'm pretty sure. You just forgot. Me too. Right? So let's see how we can derive it. Let's try that. We got 6 minutes. The sequence sum, let me call it SK. K here, number of turns. It would be, in general, initial turn plus initial turn times the common factor plus initial turn times common factor to the power of 2 plus I times R to the power of 3 plus all the way to, now, guys, question. If I got K turns, what should be the last turn? K minus 1, good, okay. You guys are good. I times R, K to the power of 1. Because you can think about this guy here is more like I times R to the power of 0. Okay. Now, how do I make progress? This is the only step you got to remember in case you want to derive the formula yourself. You have to somehow multiply the whole turn, the whole sequence over here by R. R times SK. I'm going to multiply this turn here by R. In which case, I'm going to get I times R. And I multiply this turn here by R. And then I will get I times R squared, right? And etc. I can basically align with the sequence above pretty well. Plus all the way to, there should be one more, right? That should correspond to this turn here multiplied by R, right? That one there should really give me I times R to the power of K. All right? And you can see that this part here is completely the same between the two sequences. So what I will do is I'm going to do the following. I'm going to do, let's say, R times SK minus SK. I'm going to say this term here minus this, in which case this whole part here cancel out. I get this minus this. Okay? I'll get, oh, just before that, I can factor out R. I can factor out SK, beg your pardon. I can factor out SK here, which will give to me R minus 1 times SK. Okay? And then this will be equal to basically this minus this. I times RK minus, I'll just say I right here. And then I can factor out I, which will be I times R to the K minus 1. Okay, basically, what's relevant now would be this guy here, and also this guy over here. Because I want to know what's really SK, that's my original problem. I can simply say, to get SK, divide this over that. All right? So finally, I can get something like SK will be equal to I times R to the power of K minus 1. Divided by R minus 1. Okay, I got 2 minutes now. Okay, this formula here is very general for any arbitrary value of K, I, and R. All right, However, for binary tree, you have some special value to simplify that. But you should know the general formula as well. Okay? Let's now set aside. And this will be something you have to make sure you really understand before Thursday. Okay? I'm going to put it here. In the special case of binary tree, the R, the common factor, will be 2, because every node maximum can branch out two nodes. And also, initial term will be basically the root, right? How many nodes are there in the level 0? Just one, just the root. Okay, let me make a very quick note here. 2 here simply means for binary tree, whenever you got any node here, you will branch out maximum 2 times. 1 here and 2 here, left and right basically. And the 1 here is really the root of the tree. And let's now try to simplify that. What you will get is SK initial node will be 1. And then R here is 2 to the power of K minus 1 divided by 2 minus 1. Right? I replace R by 2. And this will simplify to just 2 to the power of K minus 1. And the K here will be about a number of terms. Usually, it will just correspond to the depth of the bottom node, which I'll explain a little bit more. All right, give me 30 seconds, and then I'll let you guys go. Before Thursday, please review this formula over here, the general form, and also about this final form over here. Because for all the mathematical property that we're going to speak about binary tree, we have to refer to this formula to some extent. All right, also look at the heights algorithm as well, do some tracing, and then we'll continue from Thursday. All right, thank you.